In considering probability, we deal with procedures such as taking a polygraph test, rolling a die, answering a multiple choice test question, or undergoing a test for drug use that produce outcomes. An event is any collection of outcomes or results of a procedure. A simple event is an outcome or an event that cannot be further broken down into simpler components. And the sample space for a procedure consists of all possible simple events. In other words, the sample space consists of all outcomes that can't be broken down any further. Here's some examples of some of those probability terms. So here's a procedure, rolling a die. The sample space would be all of the possible simple events that are outcomes of the procedure rolling a die. So the possible outcomes when we roll a die are 1, 2, 3, 4, 5, and 6, depending on which of those faces come up. Another procedure would be answering a multiple choice test question. So to find the sample space for that procedure, we'd think about the different possible answers for the question. So these would be something like A, B, C, and D. Another procedure would be undergoing a drug test. And the possibilities for the outcomes of the drug test would be either that it's positive or it's negative. So that would be our sample space. Another procedure would be to look at the births of 3 children. And the sample space in this one is a little bit more complicated because we're actually looking at the genders of the 3 children. And in fact, we're even including what order the genders happened in. So our sample space would be these 8 possibilities. Either we had 3 female children, or we had a female, and then a male, or female, male, female, and so on. So we've got a total of 8 possibilities as events in our sample space. Now, in that last procedure, the event of 2 females and 1 male is not a simple event because that could happen in 3 different orders. So it could be broken down into 3 simpler events. So either the 2 females came first and the male came last, or the male was in the middle, or the male was first. So there are 3 different possible ways that we could get 2 female children and 1 male child. Now the outcome female, female, male is a simple event because it can't be broken down any further. Now the notation for probabilities, a capital P denotes a probability. We usually use capital letters to denote specific events, like A, B, and C. And P of A denotes the probability of event A occurring. So approach number 1 is the empirical approach, or we can call it relative frequency approximation. So in this approach, we conduct or observe a procedure and count the number of times that event A actually occurs. Based on these actual results, the probability of A is approximated by looking at the number of times event A actually occurred and dividing that by the number of times the procedure was repeated. This is why it's also called the relative frequency approximation approach, because what we're finding is the relative frequency of event A. Approach number 2 is called the classical approach. In this one, we assume that a procedure has n different simple events and that each of those simple events has an equal chance of occurring. This is a requirement if we're going to use the classical approach, is that we have to be able to break our procedure down into outcomes that each have an equal chance of happening. So in this situation, if event A can occur in S of these n ways, then our probability is S over n, or in other words, the number of ways that A can occur divided by the number of different simple events in our sample space. Again, if we're going to use this approach, we have to make sure that the outcomes are all equally likely in our sample space. The third approach is subjective probabilities. In this one, the probability of event A is estimated by using knowledge of the relevant circumstances. So the question is, which approach should we use in a specific situation? Again, the classical approach requires equally likely outcomes. If the outcomes aren't equally likely, or if we don't know anything about the likelihood of different possible outcomes, then we can't use this approach. If we have data, in other words, results from many repeats of a procedure, then we can use the empirical approach to approximate probabilities. And if we have enough knowledge of the circumstances to make an educated guess, we can develop a subjective estimate of the probabilities. Here's some examples. First, find the probability that a randomly selected car in the United States will be in a crash this year. Well, in order to do this, we would need some kind of data. So for a recent year, there were 6,511,100 cars that crashed among the 135,670,000 registered in the United States. This is based on actual data from the Statistical Abstract of the United States. So using this data, we can use the empirical approach. The probability that a randomly selected car will be in a crash this year would be the number of cars that crashed from our data divided by the total number of cars registered. So that would be our 6 million and some divided by our 135 million. And this gives us a value of 0.0480. Now in this one we couldn't use the classical approach since our two outcomes, and that is that the car crashes or that it doesn't crash, are not equally likely. Really the only thing that we have is data, and so there's no way that we can do anything with equally likely outcomes in this one. Here's another example. Find the probability that in 3 coin flips you get exactly 2 heads. In this one we can use the classical approach because we can assume that the coin is fair, so there's a 50% chance that in any one flip that you'll get a head, and there's a 50% chance that you'll get a tail. Since we're doing 3 coin flips, we actually end up with 8 simple events in our sample space. This is a lot like the example we looked at earlier with the 3 children and them being male or female. So the 8 possibilities in the 3 coin flips are either that we get all heads, that we get head, head, and then a tail, or that we get head, tail, head, and so on. So these are all 8 of our possibilities. We can assume that each of these outcomes is equally likely. And we're looking for the probability that we get exactly 2 heads out of our 3 flips. So if we look at our events in our sample space, the ones that have 2 heads are head, head, tail, tail, head, and tail, head, head. So that tells us there are 3 ways out of the 8 in our sample space that our event can occur. That means our probability would be 3 divided by 8, or 0.375. Again, in this one, all we're doing is figuring out how many ways our event can occur, and assuming that each event in the sample space is equally likely, we divide by the number of events in the sample space, and that gives us our classical probability. One more example. A survey asked this question about Kentucky Fried Chicken. Will KFC gain or lose business after eliminating trans fats? Among the responses received, 1,941 said that KFC would gain business, 1,260 said that KFC business would remain the same, and 204 said that KFC would lose business. Find the probability that a randomly selected response states that KFC would gain business. So first, it'd help if we had a little bit of summary of this information. So we had this many responded gain, this many responded the business remains the same, and 204 responded that there was a loss. The total responses were 3,405. Since we have this data, we can use the empirical approach to find our probability. So the probability that a randomly selected response says the business will gain would be the number out of all the responses that said there would be a gain in business out of the total number of responses. So that would be 1,941 divided by 3,405, which is 0.570. Let's talk a little bit about possible values for probabilities. Again, a probability is a measure of the likelihood of an event occurring. So we've got a range of possibilities for our probability values. Starting at the bottom, if our event is impossible, or it's something that can't happen, then the probability is 0. On the other end, the probability of an event that is certain to occur, or that has already occurred, is 1, or 100%, if we want to put it in percentage terms. And then we have all these possibilities in between. If the event is unlikely, we would have it down here with a small probability. If it's likely, we would have it up here closer to the 100%. One value that a probability can't have is a negative value. So we can't have any probabilities that are less than 0. We also can't have probabilities that are greater than 1 or greater than 100%. In this class, we'll define an unusual event as one that has a small probability of occurring. And in this class, for the most part, we'll use 5% or 0.05 for our borderline for unusual events. So if the probability is less than 5%, we'll say it's an unusual event. Here's some examples of basic probabilities, and these are ones that we might hear about or see a lot. For example, there's a 70% chance of rain today. The probability of getting tails when you flip a coin is 1/2 or 50%, assuming that the coin is fair. The probability of Thanksgiving Day falling on a Wednesday next year is 0. The probability of Thanksgiving Day falling on a Thursday next year is 1, or 100%. And the probability of winning the grand prize in the lottery is very small. It was 0.00006 in the example we already looked at. This would definitely be considered an unusual event.